My name is Matt Williamson. I'll be your host today. First, start by introducing our speaker, Derek Jacobs. Then he will give his presentation, which will be about 30 minutes, followed by a short question and answer session. If you think any questions during the presentation, please enter them into the chat box at any time, and we'll go through some of those at the end. So now, first of all, I'd like to introduce Derek Jacobs. Derek is a seasoned professional and structural engineer with over 16 years of experience. Since joining ADF Engineering in 2011, he's worked on various projects, including facility building additions, equipment access walkways, and foundation systems. Derek's expertise covers structural condition assessments, OSHA compliance, wind and seismic design. He is skilled in personnel management, project definition, proposal development, and cost estimation, as well as collaborating with contractors and providing on-site construction support. Now I'll turn it over to Derek for today's presentation.
All right, thank you, Matt. Welcome everybody. Happy to be here. I'm gonna kind of be going over this talk. I've given it in person a few times at a few different sites, so hopefully it comes pretty easily, but I'm used to doing it in front of a live audience, so bear with me. And yeah, like Matt said, if any of you guys have questions, feel free to put them in the chat, and I can stick around afterwards as long as I need to, and we can get all those answered for you. So I will see, make sure I get that. Nope, wait a minute. Click the right window there. There we go. Okay, so I think first I always start with, a lot of times people have some questions with what exactly does a structural engineer do? I know there's a lot of times there's also a little bit of confusion between structural engineers and architects. And I'd say that architects do a lot of like planning for life safety, a lot of, flow of office spaces and, things like that. But the structural engineers are the ones that are responsible for essentially the skeleton of any building, and making sure that it's a solid system that stays where you want it and, does everything you need it to do. So yeah, we here at ADF, we're mostly with industrial design with our plants. So we do a lot of steel work, a lot of concrete, not a lot of timber, but it has been done for some salt buildings and plants and stuff like that. But we get into a lot of towers, buildings, equipment supports, a lot of access platforms. When we also get involved with fall protection and safety issues too, because a lot of times that does have a structural impact. So when we start a project, the first thing we really need to do is determine what kind of load that we're going to be dealing with and how much. A lot of the projects, again, like we do, and a lot of the stuff we see on sites is related to a process upgrade. So we will have a lot of ideas of what the equipment needs to be, what the changes need to be done there, and we will have to look at it in terms of what does all this weigh? How much space is this going to take up? And that kind of sets our structural basis for design. So we look at things like, what building code we're dealing with. We look at the site-specific information, such as the geological stuff, if we have foundations and questions. And we'll look at, what the existing buildings are, if there are any. And I'll kind of touch on that more later. And then, sometimes there's stuff like cost schedule restrictions we run into a lot, and even some limitations on height, and depending on the area the building is in, there can be other things there. So we have to take that into account, and then we'll generate that preliminary design. A lot of times that goes through gate reviews or costing phases, and then while we're receiving the final equipment information, and once that all comes in and those layouts are approved, we'll finalize that design and issue it. We're kind of going into the meat of the presentation today. I'm going to be covering a lot about terminology and how that terminology affects or comes into play with drawings, and what you can see on drawings, and what a lot of these words you hear when talking to a structural engineer that maybe don't quite make sense, or not fully understanding what they're referring to. We'll try to cover all that. So for us, there's different type. When we talk about a load and what we're trying to support with the structure, there's different types of that. The terminology here is dead load is almost our most common. That's the weight of the structure itself, and any permanent weight that's going to be in that structure, such as equipment, or any kind of heavy furniture, occasionally, or anything that's just going to be not kind of a transient piece. Live loading is the second most common, and that is the weight of people, storage, product weight inside of buildings. So those are the loads that kind of come and go. You might have one person walking around, you might have 50, but we make an assumption based on a lot of codes that what we're designing each thing for, and so that comes into play. And it kind of depends on what the structure is specifically, and we'll look at that in a little bit on what we're going to assume that live load is. Then the kind of more difficult loads, dynamic loads. I'm sure you guys know a lot of the equipment that you might be dealing with has what we call like a vibrational or dynamic load, where such as like a Rotex screener or a conveyor, or some type of drum, or fans are a big one. Fans, we like to think that we prefer them not to vibrate, but occasionally they do. And we want to make sure that whatever structure that they're sitting on isn't going to be negatively affected by that. So we always try to take that into account too. And all those are kind of vertical. Those first three are kind of all vertical loads. They're affected by the weight, by gravity. And then we kind of get into what we call our lateral loads. And those are kind of resolved in a different way. That's kind of like a side-to-side loading for the most part. That's going to involve your wind, your seismic earthquake forces, and then the last one is we have like thermal loading, and a lot of this is if we have big piece of equipment or piping that has a big thermal temperature change, they can expand, and if we aren't careful with our supports of those pieces, the expansion can do damage or cause to itself or to the structure surrounding it. So we try to leave those changes or that thermal growth free to move. And how does this affect how do these loads show up on the drawing? So usually you're going to see them in one of two ways. On the cover page, there's going to be a design data kind of information dump, as it were. And you see here, this is an example of one of our projects. We provide both kind of the live load. We talked about that live load. What is that? It kind of differs depending on what area you're in. A lot of times this will be kind of required by this ASC 710 or 16 or whatever year version that is. Most industrial floors are somewhere between 60 PSF for a catwalk, walkway, or a light floor. 100 pounds per square foot is common, all the way up to maybe 200 if it's being used for storage. And then roofs are much lighter, and ground floor is heavier, and that's usually like a slab or something anyway. So this information is important when both you're kind of looking and trying to think about making changes to a structure, or if you're having another project something come in, you want to make sure you keep that information. So one of the things I'm going to be bringing up quite often in this presentation is that we don't see very often is that people that don't keep their structural drawings. So you have a plant that's built. A lot of times they'll keep maybe the general arrangement equipment layouts, but they might not keep the structural drawings, and those are always going to be helpful, not only for the structural engineer coming in to look at any kind of modifications, but also for the engineers working on site to understand what the structure that you're in was designed for and what the intents and purposes was. So If you're planning on putting storage, for example, in a certain area, and you have the drawing and it says that that was only designed for a light floor load of like 60 pounds per square foot, then you have to maybe contact the structural engineer, see what you can do to make that change and get that upgraded. But other information on here too regarding snow loads, which is obviously an outside on the roof. So there's different load cases there between live loads on the roof and snow loads on the roof, and then we put on information regarding what was assumed for wind and seismic forces. Sometimes it's not shown on like a big collection like that, and we'll have individual plans and views of each area, and we'll show it here on the right where we have basically a title. Right below the title of a view, we'll have information on there. And a lot of times that is to show both maybe the live load that's assumed for that specific area if it's not consistent throughout the building, and also what the equipment weight is in a particular view. So if you have a platform that's supporting, 3 pieces of equipment, it is nice to have that information on there too. So we can both, if an upgrade is occurring and we know the weight of the new equipment, or maybe we don't know the weight of the old, or we can at least know what was assumed for the design of the floor. And if the new equipment is significantly more, we know that potentially we should have a structural engineer come and evaluate that. So when we get into these drawings, we have different types of views. Sometimes it's not clear necessarily what all they mean. So the first one is a plan view. That's the most common. You're going to see you have a top-down view from above showing all of the horizontal framing. A lot of times we'll also include equipment locations and floor openings. It kind of looks like this as an example. You'll see column lines as a reference in the building that'll go up, up and down, north to south, left to right. Usually north is up in these views, but not necessarily. But you'll have both orthogonal directions, column lines shown, and those will serve as a good reference point for contractors and things like that to be able to find where these things are supposed to go. We also have elevation or section views, which are kind of the same thing. That's a side view showing additional information. Here we have elevation views, although they're called out as sections, but this is more of an elevation view, which will show like the entire full view, partial to full view of the entire structure height. So if you have a full building, the elevation view will be like if you were standing outside of the building looking at one wall, what you would see. A section view is usually a smaller cut. I think this was like an indoor platform, so it was just a view, section cut, but it's a side cut, generally taken from a plan view that gives more frame of reference, and by providing a secondary look at an object we're trying to show on a drawing. Details are the last one, where that is more of a similar to a section, but usually a blown up view from plan. So instead of taking it from a different angle, it's just a zoom in to be able to provide additional information, such as small dimensions to bolt spacing or welds call out or plate thicknesses and things like that. And it's kind of demonstrated here on this slide, where we have a plan view on the left of a small platform, and then you can see there's a section cut that is number 1 there that we've also shown from the side. So that's a side view of the platform. The platform is at this 580-foot-6 elevation. So you see that kind of in the section view, you'll see the bottom of the steel from the bottom level of steel from the side, and you can see the hangers that support this platform, as well as some bracing. And then the detail shown is a blow-up view of kind of the areas circled here to indicate how that hanger is meant to be connected to the framing. It all kind of ties together, and a lot of times there's references on these drawings. You can see that the call outs for the section, if they're not on the same page, the number will match to a section view number, and the drawing number of that view, or where that section can be found, is usually shown on that detail. So you see here it's sheet 411, which I think these are both in the same sheet on this case, so they're they were referenced together. Now we get into kind of terminology with steel and the shapes that those are. I know a lot of people, and we hear it, and we always understand what you guys are talking about when everyone always says I-beams, and that is, a common way to call it, because they do in fact look like eyes, the most common ones you see. But in reality, the way those are designated are usually W shapes. The W stands for wide flange shape, the flange being the top and bottom horizontal sections. And then the vertical piece is what we call the web. So you can see here, there's a couple different eye shapes shown. There's W's, S's, you might see sometimes too. There's a couple other ones called H's that are used for steel piles and things like that. The rest of the shapes are a little bit more intuitive. A C shape is a channel shape and looks like a C. An angle is designated with an L, and it looks like an L. WT is a T shape or an ST. Those are made from cutting a W or an S shape in half and getting the T shape from that. And then you have pipe sections, which, there's process pipe, but there's also structural pipe shapes, square HSS tubing, or rectangular, and then bars and plates. So the way those wide flanges are necessarily called out is two numbers. In the example I've got here is a W8 by 13, which is a very common size to be seen in plants. The 8 stands for 8 inches deep, which is the height from top to bottom of the beam. And the 13 is the weight of the beam. So it's 13 pounds per foot. Now that doesn't tell most people much, but it does help kind of identify some of the other dimensions, because they are all standardized. So we can usually translate one way or the other. If we measure a beam and know that it's 8 inches and know that the flange is only 4 inches wide, we can usually tell that that's an 8 by 13, because there's only generally a few sizes in that combination of height and flange width that relate. So there's a couple other measurements you can take to figure it out. HSSs and Ls are a little more clear on how they're identified. It's just the full dimensions. For example, an HSS 10 by 3 by a quarter is 10 inches deep, 3 inches wide, and has quarter-inch thick walls. Plates are usually designated by their thickness, and then their short side, or the shortest dimension, then by their longest dimension. And we use steel. It's pretty common because it's good ductile behavior. The slow yielding deformation, if it's failing, leads to, instead of a brittle collapse. So if something's going wrong, it gives people time to evacuate. It's good in both tension and compression, and it has a very high strength. So another good terminology for structural is what we call a kip. It's a unit of measurement. It's equals 1,000 pounds. So the strength of steel in this case is usually 50 to 36 KSI, or 50,000 to 36,000 PSI, so pounds per square inch. So it's pretty strong. Generally, you'll see that. How does that show up on the drawings? You'll see plan views like this with the sizes called out. So I've highlighted here, for example, is a W12 by 16. That's a beam. And on the right, you can see that as that relates, that's a 16-inch or 16 pounds per foot beam, which is 12 inches deep. And we know that a 12 by 16 has a 4-inch flange and a wide flange and a quarter-inch thick web and flange. So we can measure those up and be able to identify this. But again, it's always better, if it's an existing beam, to have the drawing so we're sure. Right. So concrete is another one, obviously, that we're using quite a bit. A lot of people too sometimes don't understand the difference between cement and concrete. Cement is an ingredient in concrete, Concrete is made up of cement, an aggregate such as rock, and typically rock and sand, and then water. So those ingredients make up concrete. Cement on its own is just a powder. And when you add all those together, you actually get a chemical reaction. Cement or concrete doesn't dry, technically, it hardens. So it keeps hardening for quite a long time, mostly up to like 21 days. It's very strong in compression. Usually, when you'll see concrete specified on drawings, it's by its strength, which is called F prime C, and that's mostly between 2,500 and 5,000 psi. So you'll see that concrete it's weak in. Problem with concrete though, it is very strong in compression, but it's very weak in tension. So to counteract this, we introduce rebar, steel rebar, which again, from the last slides, we know is very strong in tension as well. And that helps provide strength to the concrete members in the tension areas. So we put that in there and it keeps everything locked together. We put enough reinforcement in it to keep the concrete from cracking and also to resist any kind of bending if that's an issue. There's lots of different admixtures that you can put in concrete. A lot of times that will be called out on the drawings as well. The most popular one probably would be what we call an air entrainer. That's usually specified on the notes, and that's to protect against freezing and thawing. It's basically just soap bubbles, but it makes little pockets of bubbles in the concrete that you would think decrease the strength, but it actually allows places for water, since concrete is porous, to enter into the concrete, and if it freezes, won't expand and crack the concrete. There's other admixtures that increase the flowability and increase or decrease the set time of the concrete based on what your needs are, and help reduce the shrinkage. That's shown up on the drawings. Concrete usually this way. You'll have a plan view on the left here. You can be called out with if it's just a big mat of concrete with a thickness and reinforcement. And I was going to say, yeah, I think I maybe skipped the part with the reinforcement specifications specified by a number. It's usually 3 to 10. The number is the bar diameter in inches times 8. So if you have a number 4 bar, or the divided by the half-inch diameter. So it's the diameter times 8. So a number 4 bar would be half-inch diameter. A number 8 bar would be 1-inch diameter. So you'll see that on these views where we'll call out. It's usually specified with both the rebar number first and then the spacing of the bar. So you see on this view here in the right, the detail we have number 5s at 12. We also have instances where we have just single bars called out, or as number 6, like the number 6 is here with the parentheses. So there's 6 bars continuous into the page here as well. So a lot of times, like for example, this mat shown on the left, 5 at 12 each way, top and bottom. And we'll send you guys out a abbreviations list for drawings too. I think that'll be helpful at the end or in an email later that kind of explain a lot of these abbreviations you see. But EW is each way, T and B is top and bottom. So you have number 5 bars going at 12-inch spacing going each direction in both the top part of the slab and then the bottom part of the slab. So that's what that's telling you. All right. So I have a couple quizzes. I don't necessarily I'm not going to go through and make you guys answer them, but I just want to have you take a look at some of these. I'll give you half a second, think about them, and then we'll move on. I'll give you the answer and we'll go on. So for this first one, kind of going over what we talked about, an operator standing on an elevated platform would be considered as what kind of loading? Dead, live, seismic or dynamic. So I'll give you a beat to think about that one. You can see if you got that. So that's going to be a live load, right? That's not a permanent load. You know, that person's not there all the time. So we would consider them as a live load, and they're working. So once we have all these materials that we use, the steel and the concrete, now we have to figure out the load path. We talked about how do we design for these loads that we're going to be looking at, and how do we get them through the structure and essentially into the ground. And a lot of the terminology that people use here, hopefully this slide helps clear up. We hear a lot of times about beams, vertical beams. We'll call that a column. So if you look here, if you have a load in the middle, that load is going to be transferred kind of on this red line here through a point through the floor slab to a beam, and it'll be kind of distributed evenly between each one. So it goes to a beam that frames into another beam. Is the beam that beam is a girder. So girders are beams that collect load from multiple beams, and then the girders transfer that load to the columns, which are the vertical portions that transfer the load from whatever floor all the way down to the foundation and then ultimately into the ground. The other loads that we're dealing with, besides the vertical loads, is the lateral loads we talked about as far as wind and seismic going. So we have what we call bracing that provides that stability. This limits the drift. So it's not just active loading, it's also preventing the building from racking. You think of, if you have a, all pinned connections in the building swings side to side, nobody wants that. So it's not just a strength issue, it's also what we call a serviceability issue. If you're on the top floor of a large tower and it sways quite a bit, that's obviously going to be very uncomfortable for the worker, and we want to try to avoid that. So there's a couple different ways we can do bracing. That's probably what you'll see most in plants. And kind of depending on what equipment or what use through that bay is needed, we'll adjust our bracing accordingly. If there is nothing going through there, we got lots of room, we'll put in an X brace, which is probably the most economical. And this is because each of the two diagonals only takes a tension, so you don't have to worry about it buckling at a long length. Think of it like when you see like pre-engineered metals buildings. Sometimes you see cables being used in this way. It's like a rope. It's very good in tension, but in compression, it'll just fold in on itself. But this allows you to use much smaller sections of bracing. Unfortunately, it's one of those situations where, like, if you want to come in later and remove one, you can't just remove one and leave the other, because the other one won't be able to take the load from the other direction if the wind were to reverse. If we want to be able to have one brace that takes it, we have to design that for both tension and compression. And that's possible. It's fine to do. It's just going to be a larger section, big enough to resist buckling over whatever length it's in. And then there's other configurations like this V-brace if we have like a roll-up door, or potentially a lot of times you have like a conveyor moving through a bay. And that needs to be avoided, obviously. So we'll brace it, we'll arrange the bracing as needed. Then we can do other things like shear walls with concrete or block, or make the connections to beam to column, what we call rigid joints or moment connections is also a possibility. Those are just a large fabrication cost, and install is a lot more because they involve a lot of bolts and welds and stuff like that. So once we get through the steel structure, we come into what the foundations. So the foundations are the underlying portion of the structure that's supporting the building, transferring those loads to the underneath. For these, we always rely on the information provided by the geotech, the soil boring. So that's why a lot of times if you're dealing with structural engineers, we'll ask if there's a soils report on the site, and that way we can know if we don't have one. We always like to get one, and we can always help with that too. kind of identifying for the geotech what we need and what we're planning on doing design-wise, and that gives them a lot of help on being able to recommend, what design values that we should be using. If it's pretty good soil, we'll be able to do a shallow footing. Mat foundations, these are just square footings that spread the load out from a single column, or mat foundation, which maybe has multiple columns, or a piece of equipment like a tank, and that's just sits fairly shallow in the earth, and nothing more else is needed. Deep foundations, we're going to have piles that go deeper to either better soil or potentially even bedrock, and that gives us, usually we have to use those if like the top couple, 10, 12 feet of soil that you have out there is, according to the geotech, very low strength. And this is kind of what that looks like. We'll give a report to the geotech, we can provide these drawings like this that show where those borings are needed, depending on where the work can be. So we usually coordinate with them. Welded or bolted connections. This is usually an either or for the structural designer. We can go with both. I'd say welded connections are much easier when you're dealing with existing structures and you're trying to attach to those, but that's not always the case. Field drilling is possible. There's some pluses and minuses you can see here on between the two, but the one thing I will want to point out regarding welding, and I also have a symbology sheet for welding that I'm going to include with the handouts that come with this later. But the main one that you'll see on the drawings that I think you guys all want to look for is down here on the bottom, this field weld symbol, the flag shown on there. That means that the weld, if you see that flag, that means the weld is meant to happen in the field on site out there. As opposed to not having the flag, which means whatever we're looking at is being welded up in the fabrication shop. And I make that distinction because I know a lot of sites, obviously field welding, field cutting, things like that are much more of a deal, in terms of fire protection than not. And it's always good to be clear. I think it'd be helpful for you guys when you're looking at these drawings, if you see that symbol and you know that field welding is going to be a problem, to talk to your engineer sooner rather than later and maybe try to come up with a bolted alternative. Lifting systems. This is just a little handy guide. Talk about it a little bit in terms of terminology for those. I hear gantry a lot. I hear monorail a lot, and it doesn't always mean what we're talking about. So a bridge crane here, you can kind of see a picture. It's multiple rails with a one bridge beam going across with the hoist on it. A monorail, I've got a circular one here shown, but a lot of times you'll see those on site and they're just a straight beam. But a straight beam hung from the ceiling with a trolley and a hoist on it would be a monorail. The gantries are kind of movable monorails that have their own supports and wheels. And then a jib crane looks kind of like this, where it's an arm that's either has its own base or is mounted to an existing column, but it kind of swivels out on its own. We do a lot with fall protection. The 5,000-pound rating is, most people I think know about that, but it's actually for a self-retracting lifeline system as opposed to a lanyard. Only needs to be designed for 1,800 pounds if you're having an engineer provide it. And we recommend these a lot because, as you can see from the charts below, not only is it a lower rating and lower requirement and lower force on the structure, it's also a much shorter fall distance. And I think a lot of times people get worried about whether or not a point above can support 5,000 pounds and aren't looking at the fall distance and whether or not that they have that amount of room. So this is an important one to look at too. Just some other quick terminology here. I won't go over it too well. The one I will point out with is girts, which are the horizontal beams on the walls. Those are beams. They're acting as beams as if the normal floor framing does, but they are providing support of the wall system or panels or siding or what have you against wind. So they're actually bending in a horizontal direction to transfer that load from column to column. So you'll see those a lot too. All right. So a quick quiz. It's okay to remove one brace of an X brace configuration if the other side is still able to be left in place. So you think about that one. And that is false. Those are, like I said, those are only each designed to take tension loads. Usually, if it's designed as an X brace, the length is going to be too long for the given section to resist buckling and compression, like a cable would. I'm kind of talking about it a little bit as I go, but brownfield projects is a big word we throw around here. It is the majority, I think, of the work that we deal with, and I think that a lot of you guys deal with as well in terms of making changes to an existing site. These are always challenging in their own right. Everyone's a little bit different, so that's kind of what makes it exciting. Each one has its own uh, you know, limitations such as shutdowns and timing and, potentials for, unsafe chemicals and explosion problems. So, and then again, a good reason to keep your structural drawings, because if you're going to be modifying something in the future, it's always better to have that. A little quick bit about reinforcing. So when we're dealing with these brownfield structures, we are potentially going to have to reinforce something into if you have a floor and you're going to increase the weight on it substantially, there's options to replace the beams. But if it's maybe one or two under a specific piece of equipment, and it'd be much more of a hassle to take the beam out and replace it with something else, we'll reinforce it with more steel pieces. This is usually timing wise, this is much quicker. But the labor cost per ton is a little higher because it's a lot of welding. And this is one of the instances where probably field welding would be unavoidable because the way the requirements of how these things have to be attached. And concrete can kind of be done the same way. It can be expanded sometimes. But when we're doing these brownfield projects, previously it was all tapes and measures and eyeballs. Now we are working with laser scanning, so you'll hear that sometimes with the drones and tripods and fancy cameras. We also have, before everything was hand drawn, and now everything's done with modeling software. We use Autodesk Revit, but there's plenty of others out there, and that gives you the ability to model some of these existing and new stuff. Looks like this. Get pretty fancy. And then when we take that scan, that laser scan, we'll get that point cloud. We'll get a good visual of the existing site, and then when we want to add in new steel or add, or equipment or whatever it is, then we'll be able to look at it together. And this is much more accurate than previously with a tape measure to be able to identify any potential interferences and things like that. So it's a tool that you use a lot. Once all that design is done, we get to the drawings, making the drawings. We have design drawings. So the structural engineer will be providing you design drawings. These are to show the intent of the engineer, and when we issue them, that's kind of the start of the construction phase. A lot of times they'll have a cover page. This is where you're going to find out your specifications for building materials, steel grades that we talked about, your concrete strength, your finishes, the design basis, maybe a legend for your symbology, an overall view of the project, and then a key plan. If it's a small little platform, that key plan is really helpful to identify to your contractor where this is in the, maybe quite a large facility. So as those design drawings are sent out for feedback and pricing, usually they were stamped for review if they're not complete yet. Not for construction. These revisions are each labeled with a letter, A, B, C, etc. Once they are complete, we'll issue for construction Rev 0, and then any changes after that are going to be marked with a number and clouded so that the changes can easily be spotted. What comes from that will be those drawings are going to be sent to the fabricator or a detailer, and they're going to end up creating shop drawings. Now, these are more of what the contractor is going to use out in the field to assemble everything. So they'll have assembly sheets that show them where each piece is going to be marked, and it gives a fabricator a way to know how each beam is specifically cut, and then has a piece mark, and then there's an erection sheet that the contractor uses to know where each piece goes according to those plans. So it's kind of like a puzzle piece, or a puzzle with a legend. It shows where each piece goes. And we talking a little bit just about construction phase support. It's always good to have the structural engineer involved throughout both design, obviously, but then also construction as well, to mitigate some of those last minute changes or revisions that have to happen because site conditions may be possibly changed or equipment was different. Then anything happens, or we can also help provide a lot of feedback to the contractors if they want to have kind of material substitution and stuff like that. I have a little bit here about a condition surveys. I'll kind of skip through it pretty quick. It's something we can do if there's not necessarily a project happening, but maybe it's an older site that looks like it needs some kind of upkeep. We'll walk it down. We'll see some stuff like this. A lot of you guys probably have seen these things like this around your sites where you have some steel that looks like it's not really hanging on by anything anymore, or maybe had a oops and somebody hit it with a fork truck or something like this. So we can take a look at those and provide guidelines on, if it needs to be resolved immediately or when, if it needs further engineering assistance to do so. And if it does, we can also have the structural engineer provide those details like this to help with that. All right, last one. It is all right for a contractor or fabricator to make changes to the structural design but only if there are good contractors, or if there are little changes, or if they've been submitted to and approved by the engineer, or never. So the answer to this is C. So site conditions can vary. We understand that. Product substitutions can save client money, but any unapproved changes or misunderstanding of the design can have serious effects. So a lot of times this comes into just like, can we use a different kind of decking, different kind of anchors, different kind of paint? That's all fine. We'll look at that. But one I did want to mention, this little case study to kind of wrap us up on like what happens when there is that breakdown in the communication between the fabricators and the engineer. So this is the Hyatt walkway collapse, which is kind of a famous situation for structural engineers. We always hear about this. Built in 1978, failed about 3 years later. It was two large pedestrian bridges. It's kind of one above each other, stacked above each other. And during a party at the hotel, the lower bridge collapsed, killing about 114 people and injuring a lot more, you can see. Was one of the deadliest non-deliberate structural failures in American history. And what happened was that the fabricator wanted to alter a connection design, which is what you see here. And unintentionally offset. Just it would be in a simplify constructability, which we understand, and it's something that is always good to have checked, and make changes for that. And the engineer can work with you. But this change was kind of made. Was approved, but wasn't really understood what everyone was doing, and ended up doubling the force on a single nut on the design, and it ended up failing, and the whole bridge came down, unfortunately. But it is an example of the importance of accuracy and detail, and both showing the intent from the engineer, the shop drawing review process, particularly regarding these types of revisions, stuff like that. Yeah, so in summary, structural engineers, we design these structures to be safe and economical. But we have to be able to do that. We need to predict the forces that could be present, and fully understand the structure. That so that includes we are always asking for all the equipment information in our cases, and also what kind of existing drawings, what information do we have on the existing structure, which is another reason to keep your structural drawings. So I think that's the end of it. Well, if we're good on time, we can go into some questions.
Thank you, Derek. Now we're going to open it up to the audience to ask questions. Derek covered a lot today, and I'm sure you have a lot of questions. So we'll give it about 30 seconds to a minute so you can enter questions into the chat box if you have any. We do have a couple of polls. One, how comfortable are you with reading and interpreting structural drawings? Very comfortable, average, not comfortable. The second one we've got in there, what types of structural materials do you encounter most frequently in your work? Whether that's structural steel, concrete, masonry, or wood. And what resources do you use to ensure that construction aligns with the information provided in the structural drawings? Contractor, project structural engineer, or construction manager? So if you get a chance, if you could respond to these polls. I do have one question while we wait on that. One person's asking, how much flexing is considered acceptable with X braces? Is there a spec?
Yeah, so there's a in terms of buckling, or in terms of, I guess, so there's a what we call the KL over R ratio, which is basically just a value that's determined by the length and the shape of the brace, and it is the limit for a tension piece like that is generally to be 300, which doesn't mean a whole lot if you it's kind of a unitless measurement, but there is a spec or a requirement kind of for it in the steel code, and it's really mostly in tension to prevent it from it's not necessarily a strength issue. It's more of kind of a serviceability issue. It's kind of like you don't want it to be unsightly and kind of so flimsy that it's loose and wiggles around. So that's kind of why when you see angles back to back as bracing, there's a bolt in the middle to hold them, kind of keep them pinned together. All that's really doing is keeping that ratio down. As far as maybe if you mean what is it for, if it's going to be in compression, because there's really no deflection in if it's in pure tension. But if you're looking for potentially taking a member that wasn't X brace and utilizing it as a single tension or compression member, there is a ratio, same ratio actually, but limits 200, and a value of that is used to calculate the strength of what that member would be in compression. And that way, that's a way you could, if it's something that's maybe a little beefier, you could maybe potentially look at, okay, is this strong enough for compression? And maybe it's close enough that you could kind of like what we talked about with the reinforcement, um, reinforce it so that it's strong enough and you can take the other one out. So
Okay, couple other questions. Would you briefly describe the differences in strategies for design for stiffness versus yield designs?
yeah. Okay. Yeah. So I'd say a yield design, it's kind of the difference between, I think what you're kind of getting at is the difference between what we call strength design and serviceability design. So obviously, yield design is a strength issue. If the beam goes into yield, it's going to potentially not this, not right away, but it's going to be potentially susceptible to failure and strength, where it would, you'd have a structural failure. As for stiffness, that could be something where, the beam's got plenty of strength not to ever collapse, but if you have maybe a heavy vibrating load on it, the beam can support that load, but not without deflecting a decent amount. So that's a serviceability issue because we don't want anyone walking on that floor and having it vibrate and then, being uncomfortable with the amount of floor, or even like a small platform. I know we've all probably been on catwalks up on conveyors hundreds of feet up in the air. That conveyor bridge might be strength wise sufficient, but if there's a stiffness or deflection issue, um, then also that's a problem. So that's something we look at. There are limitations. Obviously the strength comes into code wise, as we don't want failure, but there's stiffness limitations. Usually it's something along the lines of the length of the span of the beam divided by 240 is the maximum amount of deflection you would want to feel in it if you were kind of walking over it. So we have values that we look out to kind of make sure that it's both the strength sufficiently strong and both comfortable to be operated on.
Does the bracing design take into account dynamic loading from rotating equipment in operation inside the building? If so, how would you quantify that on a macro scale?
Good question. Okay, so the there's kind of two different kinds of bracing, or I'd say you have when you look at most building bracing, you're going to what we call it's the main wind force resisting system. Uh, it's the transfer, that load path we talked about for external forces acting on the building, uh, and that's a lot of that's designed for that. I think that's kind of the main focus on that. Though I would say that if you had a significant um, vibrating piece of equipment and it was tied uh, in a sufficient way to the building, it would definitely be a load case. So we look at multiple load cases when we design structures. Usually, it could be just dead load or dead load plus live load or dead load plus live load plus wind or dead load, plus this dynamic load, that kind of thing. So it'd definitely be involved if we knew what that would be. And we do get that a lot. There's the dynamic load on equipment isn't always vertically up and down. And that's not always side to side, or it can be both. Um, and it's one of those reasons why we like to look at or get that final equipment information from vendors before we finalize any structural design, because that information is important. So if we have that, it is definitely factored in as part of a load case that, where that bracing would be affected by those loads and would be taken into account possibly in combination with the wind and the seismic. But yeah, and stiffness wise, it would also look at it that way too.
Can you provide an example of where square tubing would be used?
Oh, sure. Yeah, that's a good one. So square tubing we used 99% of the time in clean design areas. We have I think Matt knows all about this. He's the dust guy. Uh, we definitely want to we have dusty plants, and we want to mitigate that as much as possible sometimes. Or if we're in a food safe area, we always want to eliminate as many ledges as possible. So while wide flange beams are very economical and efficient in what they do have extra sets of ledges, and we can cover those, but it's if we have to, but it's always nice to put in a tube steel connections because or tube steel members because they do not have those ledges. It's just the top of the beam is all you really got to worry about, and usually that's either cleanable or covered by decking or something like that. So yeah, tube steel is most often not what we use for clean design areas.
Does the T and B on the rebar mat indicate a double mat?
Yes, that would be what that means. There's a if the concrete is thick enough, we would want to put a top and bottom mat. Um, if it's in large, it kind of goes into the way a large foundation like this would behave, and in bending, um, there might be bending in either direction, and so there's a tension. The tension could be on the top or the bottom, so we want to make sure we're reinforcing both sides. And even if not, it's nice to have that little bit of reinforcement at the top, close to the top, because that helps prevent cracking, unsightly cracking if you have like a floor slab or something that you want to keep nice.
Okay, it looks like there aren't any more questions, but before we conclude today's webinar, as a thank you for attending, we'll be emailing you a copy of Derek's structural terminology abbreviation sheet. If you have any additional questions, please feel free to reach out and email Derek at djacobs, DJACOBS, at adfengineering.com. On behalf of ADF Engineering, I want to thank all of you for joining us today. We appreciate you spending time with us and look forward to seeing you at our next webinar.